Hello everyone, and welcome to my channel. My name is Nick Malloy, and today we're diving into the world of geospatial science by exploring how map datums and projections impact spatial accuracy. So let's get started. In this video, I'm going to walk you through a demonstration of my tutorial, How to Understand Spatial Errors in Map Datums and Projections. You can find the written instructions for this tutorial on the Geospatial Institute website. I'll place a link in the description below. Setting up your workspace. First things first, let's set up our workspace. I'll walk you through creating a project folder and organizing it effectively. Remember, good file management is vital when working in GIS. Start by creating your project folder on your computer's desktop. You can call the project folder Exploring Errors. Be sure that there are no spaces in the name. You can use an underscore instead of a space. Inside the project folder, you should create the 3 standard subfolders I typically use: Original, Working, and Final. The Original folder is for storing unaltered copies of your data. The Working folder is either for working copies of your data or data sets you create during the project. The Final folder is for storing your outputs, such as tables, reports, and final map layouts. Setting up a project in ArcGIS Pro. Next, you should launch ArcGIS Pro. If it's your first time working in ArcGIS Pro, you might be prompted to sign in. On the ArcGIS homepage, click Map under the New Project options. When the Create New Project window opens, name the project Exploring Errors. It's fine to use spaces here. The next 2 steps are important, so don't skip them. Click the File folder icon so that your location is set to your Exploring Errors folder on the desktop. Then uncheck the box next to Create a New Folder for this project. The only time you would leave this box checked is if you started here and still needed to create a project folder. In this instance, you don't need to create a new project folder since you already did that earlier. When you create a new project in ArcGIS Pro, several elements are added automatically to your workspace files. Open the project folder in Windows File Explorer to see what's inside. You should notice that beyond the 3 subfolders you initially created, Original, Working, and Final, there are a few other items added to your workspace, such as a Geodatabase and an ArcGIS project file. Never delete any of these folders and files from your workspace, or you run the chance of corrupting your project. In ArcGIS Pro, you can see these default files in the Catalog pane by twirling open the folders. Skill Drill: Downloading data from natural earth. Time for our first skill drill. In case you're wondering, whenever a section starts with the words skill drill, it means that it's going to cover skills you have learned previously. This section assumes that you have experience downloading data from public sources. In this step, you're going to download several data sets from the Natural Earth website. It's a great resource for free vector and raster data sets. Follow along as I show you how to navigate the website and save data correctly. On the Natural Earth website, click the Downloads link. Under Small Scale Data, click the Cultural link. Here you need to download 2 data sets. The first is called Admin Countries. You can click the link to download it to your Downloads folder. However, if you want to download it directly to your original folder, you can right-click on the link, select Save As, then navigate to your original folder. Scroll down and do the same thing for the Populated Places dataset. The next dataset is on a different page. Hit the back button, and then go to the Physical Datasets page. Here, you should download the graticules, which are set to 10 degrees. Like before, you want to save this dataset to your original folder. If for some reason you downloaded these datasets to your download folder, just cut and paste them into your original folder. In Microsoft Windows File Explorer, open the original folder and decompress each of these zip files. You can use 7-zip to extract the contents. One shortcut I like to use is a right-click drag on the zip file, which brings up the 7-zip options. If you can't get that to work, then just right-click and show more options. That will get you to the 7-zip menu. Be sure to delete the zip files after decompressing them. Working with the File Geodatabase. When you start a new project in ArcGIS Pro, it automatically sets up a geodatabase along with it. Think of a geodatabase as a big box that you can store various kinds of geospatial data. It's a handy way to keep and organize data sets that are related to each other. There are a few different types of geodatabases, but the one we're focusing on here is the File Geodatabase. This type can handle individual data sets as large as 1 terabyte. Often when you use different tools in ArcGIS Pro and save your work, it will default to saving to the project's geodatabase. This is useful because it helps you keep all of your data neatly organized right within your project workspace. Up to this point, you've likely been mainly dealing with shapefiles, the go-to format for vector data. In ArcGIS Pro, a shapefile shows up as just one file. But if you peek at it in Microsoft File Explorer, you'll notice it's actually a collection of several files linked together. Some of these files are where the spatial details live, like where something is geographically. Others are like a database holding attribute data. Then there are files that record the shape or the geometry of a feature. One of the most common mistakes novice GIS users make is to separate or delete these files. If any of these parts are missing, the data won't work properly. At this stage, you'll be using the shapefiles you downloaded from Natural Earth to create feature classes in your geodatabase. A feature class is quite similar to a shapefile in many respects. It's just like a shapefile. It's a collection of geographic features, all stored in vector format and sharing the same type of geometry, be it point, line, or polygon. The most obvious differences you'll notice are in the file's structure and the size limits. Inside a file geodatabase, a feature class can handle up to a whopping 1 terabyte of data. In contrast, a standalone shapefile can only manage up to 2 gigabytes. In the catalog pane, right-click on the Exploring Errors geodatabase. Select Import, then Feature Classes. Navigate to your original folder and select the countries, graticules, and populated places shapefiles that you downloaded from Natural Earth. Leave the rest of the default settings and click Run. Close the geoprocessing pane when finished, and check your Exploring Errors geodatabase for the new feature classes. If you don't see them, right-click on the geodatabase and select Refresh. Adding XY data. To get to the CSV file, click on the provided link, which will take you to a Google Drive page. Once there, hit the Download button. After downloading, move the CSV file from your Downloads folder to the original. It's a good idea to take a moment and open the file with Microsoft Excel to see what's inside. You'll notice it's a pretty straightforward table with just the basics. There are only 2 fields, latitude and longitude. The values for these are given in degrees and are presented as plain integers. In the CSV table, apart from the latitude and longitude coordinates, there's no extra spatial information. Specifically, it does not contain any information about the geodetic datum that these coordinates are based on. It's crucial to accurately specify the datum for these geographic coordinates in order to align the data correctly on the map. The coordinates you have here are from WGS 1984, which is the datum most frequently used by GPS devices and online platforms. In ArcGIS Pro, refresh the original folder to be sure that the CSV file appears in the catalog pane. When you see the CSV file, right-click on the file and select Export, then Table to Point Feature Class. The XY Table to Point tool should appear in the geoprocessing pane, pre-filled with the latitude and longitude, in the XY fields. Check to make sure that the coordinate system is set to GCS WGS 1984. Leave all other settings as default and click Run. The centroids should be added to the map. If not, you can add them manually. Take a moment to add the cities, populated places, and graticules to the map. Rearrange the layers in the contents pane so that the graticules lie beneath the countries. Before moving on to the next step, go ahead and save your project. Skill drill, creating indicatrices using the buffer tool. Back in 1859, Nicolas Tissot, a French mathematician, came up with a technique to show how map projections can distort space. He did this using circles that were evenly spaced and identical in size on a globe. When this globe is turned into a flat map using mathematical formulas, these circles change in size and shape. This change visually represents the distortions caused by map projections. In your case, you'll be using the centroids feature class and the buffer tool to create a similar indicatrix, which will help you to understand the distortions in your map projection. We'll start by changing the map pane's display projection so that the Earth looks like a globe. We'll use a map projection that Esri calls the world from space, which is based on a true perspective planar projection called the orthographic projection. Just remember that what you see is a flat map, not a three-dimensional globe. We'll talk more about that later on. Open the map properties and navigate to the Coordinate System tab. Under XY coordinate systems available, twirl open the Projected Coordinate System option. In the Projected Coordinate System folder, locate the World folder. Right-click on the World from Space and choose Copy and Modify. By default, this map projection is centered on Europe. In this step, you're going to alter the map projection so that it is centered on the Pacific Ocean. In the Modify Projected Coordinate System window, change the longitude of center to 180. When ready, click Save. You should now see the world map using an orthographic projection centered on the Pacific Ocean. I'm just going to click the Full Extent button to fill the map pane. Now it's time to create buffers. Click on the Analysis tab, and then click Pairwise Buffer. You can find it in the Tools group. Our goal is to create a 500-kilometer buffer around a layer containing the centroids. Add the centroids layer as the input feature. Change the output name to Indicatrix. Then change the linear units to kilometers. Make sure that the method is geodesic, shape preserving. Lastly, enter the number 500 for the distance value and run the tool. Your buffers should appear as regularly spaced circles around the globe. Evaluate distortion patterns in map projections. You are going to need to document your work, so take a screenshot of your map by pressing Alt, then Print Screen. You can also use the snipping app if you're more comfortable with using that to take screenshots. Whatever you do, don't use your phone to take pictures of the screen. It never works right. Next, open a blank Word document and paste your screenshot by pressing Ctrl-V. If you want, you can crop the image so that it just shows the map pane. Copy and paste the questions from the written instructions into your Word document. As you've previously discovered, a map projection involves transforming the Earth's round surface onto a flat plane using mathematical equations. It's important to remember that this process inevitably involves a significant amount of distortion. However, certain map projections are designed to accurately maintain specific geometric characteristics known as preserved properties. The distortion, when it does occur, affects one or more of the following properties: area, shape, distance, direction, and continuity. Each map projection strikes a different balance among these properties depending on its purpose and design. Look at the map and think about the first question. Which of the 5 properties appear to be preserved based on the size and shape of the indicatrices? When I look at the world from space projection, I can see that most of the circles appear to be consistently shaped. It's only when you get to the edges of the map that these circles start to flatten out and distort in shape. So my answer here is that shape and area are preserved. The next question wants to know which properties are distorted based on the circles. We already established that area and shape are preserved. That leaves distance, direction, and continuity. It's hard to tell if distance and direction are distorted just by looking at the size and shape of the circles. Definitely along the edges. I think the most obvious answer to this question is continuity. Continuity is disrupted, since only half of the globe can be seen at once. This is a classic characteristic of the orthographic projection. Remember, the map looks like a 3-dimensional globe, but is actually a flat map that shows one half of the Earth from a faraway perspective. I think that's why Esri calls it the world from space projection. The next question is, where on the map does there appear to be minimal distortion? I think the circles appear to be less distorted along the equator and along the central meridian, which we set to 180. This leads us to the next question. Where on the map does there appear to be the most distortion? As I mentioned earlier, the circles start to lose their shape along the outer edges of the map, where they begin to flatten out to maintain their perspective. Evaluating spatial error. Before moving on to the next step, I'm going to clean things up a bit. I'm going to remove the Esri base map and the centroids so that the map is easier to see. You're going to use the measure tool, and the labels from the base map can get in the way. Same goes for the centroids. I want to be able to see the cities clearly. You should be able to see the cities layers, but there's a bug in ArcGIS Pro which hides the cities after changing the central meridian of this map projection. The good news is that they will reappear when you zoom in close, which I will show you in the next step. Go ahead and zoom in close to the circles on the coast of Alaska. On the map ribbon, open the measure tool. To start off with accurate measurements, you need to set a reliable baseline. For this, switch the measurement type to geodesic. Remember, geodesic measurements consider the Earth's spherical shape when calculating distances. Since the circles in your indicatrix layer are exactly 1,000 kilometers in diameter, make sure to adjust the units in the Measure Distance tool to kilometers. This will ensure your measurements align correctly with the scale of the circles. I chose the circle off of the coast of Alaska because the shape is only minimally distorted. It's not a perfect circle, but it's pretty close for our purposes here. Practice using the measure tool. Move the mouse cursor over one side of the circle and click once. Then move the cursor to the opposite side of the circle and double-click to complete the line segment. The measure tool records the information on the dialog box. Don't worry about getting it perfect. This step helps you practice using the measure tool while also demonstrating the accuracy of a geodesic measurement. The next part is a little tricky because of the bug I mentioned earlier. The cities layer should be visible, but it's not. So you're going to have to zoom in close to see the points. Use the mouse wheel to zoom in to Japan and locate the city of Tokyo. You can turn on the map labels for this layer if you need them. Tokyo is the dot closest to this elbow shape. Use the measure tool and click Tokyo once. Then use the mouse wheel to zoom out. It's tricky. You may need to scroll in and out while moving your mouse to get the map to do what you want. Zoom close to the border between Washington and Canada to find the city of Vancouver. When you have it ready, double-click to establish the line segment. On the Measure tool, highlight and copy the distance value. Then open a blank Microsoft Excel workbook and create the table described in the written instructions. This table lists the map projection, the distance in kilometers, and the scale factor. Our baseline is going to be the geodesic measurement, which is the one you just took. Paste the distance value for the geodesic measurement into the table. Under scale factor, enter the formula equals sum B2 / $B $2. The dollar signs will force copies of the formula to consistently divide by cell B2. I formatted these cells as a table, so it automatically copies the formula onto the next cell. Most likely you didn't do that, so you'll need to copy and paste the formula into the cell on the next row. Okay, so now you're going to repeat the measurement between Tokyo and Vancouver. This time you are going to use the planar method instead of the geodesic. It doesn't have to be perfect, but try to be somewhat accurate so that we can make a comparison between the geodesic and planar methods. Record the value and paste it into your Excel table on the row for the world from space projection. If you have not done so already, be sure to paste the scale factor formula from cell C2 to cell C3. According to our calculations, the world from space has a scale factor of approximately 0.89. So what does that mean? As you've learned, the scale factor is essentially how the principal scale compares to the actual scale. The principal scale, which is used to create the map projection, is based on the scale of the generating globe. Cartographers call the map scale that is measured locally the actual scale. In this case, instead of using scale ratios for actual and principal scale, you're dividing the planar map projection measurement by the geodesic measurement. The geodesic measurement, like the principal scale, is also based on the scale of the generating globe, making the results comparable. Here's how to interpret scale factor. A scale factor of 1 means that the planar map projection distance is equal to the spherical geodesic distance. There's no distortion in terms of distance. A scale factor of less than 1 shows that the planar map projection distance is shorter than the spherical geodesic distance, indicating that the map projection is shrinking distances. A scale factor of greater than 1 indicates that the planar map projection distance is longer than the spherical geodesic distance, meaning the map projection is stretching distances. Understanding the range of the scale factor across the map gives you a solid grasp of the potential spatial error related to the size and distance on the map. Return to your Word document and paste in the next question from the written instructions. What does the scale factor indicate in terms of distortion for this map projection in the region between Tokyo and Vancouver? The world from space projection has a scale factor of about 0.89. Since this is less than 1, we can say that a scale factor of 0.89 indicates that distances on this map projection are smaller when compared to the geodesic distances. Save both your Word document and your Excel table to your final folder. You'll answer more questions and add to the table in a later step. Skill drill. Evaluate spatial error. Now it's time to practice what you've learned. You need to repeat the steps for the other map projections listed in the written instructions. For example, the next projection on the list is the cylindrical equal area. You'll need to update the spatial reference system of the map pane from the world from space to cylindrical equal area world. You'll need to modify the projections so that the central meridian is 180 degrees. That way, the map is centered on the Pacific Ocean. Then you'll answer the same questions about the distortion patterns revealed by the circles. Last, you'll take a planar measurement from Tokyo to Vancouver and add it to the table. You don't need to repeat the geodesic measurement for this exercise. You'll use the first one you recorded on your table. Then you'll answer the last question about the scale factor. Repeat these steps for the remaining map projections. Troubleshooting datum shift. Having delved into how various projections can distort the geometric characteristics on a map, your next step is to explore how ArcGIS Pro manages multiple datasets that each have their own spatial reference systems. In ArcGIS Pro, geographic data is visually represented in the map pane. As you've already learned, the map pane operates with a specific display projection, which is set in the Map Pane Properties Coordinate System tab. Previously, you adjusted the display projection in this tab to visually assess the distortion patterns on the Indicatrices layer. It's important to note that while you were changing the spatial reference properties of the map pane, the spatial reference of the feature classes in your geodatabase remained unchanged. ArcGIS Pro can seamlessly handle these differences thanks to a process known as Project on the Fly. This process allows ArcGIS Pro to dynamically adjust and display datasets with different spatial references in the same map view, ensuring a smooth and integrated visualization of all data, regardless of the original coordinate systems. Here is the problem. When ArcGIS Pro comes across two datasets that have different spatial reference systems, it automatically aligns these layers using a process called datum transformation. This transformation is a mathematical method where the geographic coordinates from one datum are converted into the coordinates of another datum. Remember, geodetic datums are essential for mapping. They consist of a reference ellipsoid and an origin point that together model the Earth. These datums form the foundation for geographic coordinates like latitude and longitude. Without a datum, these coordinates wouldn't exist. Each datum is unique because it has different latitude and longitude values, which are determined by its position relative to the Earth's geoid model. This means that the same location can have different coordinates under different datums. ArcGIS Pro's ability to perform datum transformations on the fly is not always consistent or accurate, which can lead to a kind of spatial error called a datum shift. Unless you're looking for it, a datum shift can be hard to notice. In ArcGIS Pro, save your project file. Then click the New Map button located in the upper left side of the ArcGIS Pro window. As you can see, this opens a new blank map pane named Map 1. To keep things organized, let's rename this map pane Datum Shift. You can do this by opening the map pane properties and typing in the new name on the General tab. For this next step, we need two datasets, which you can get from the Humboldt County GIS download page. You can find the link to this page in the written instructions. The first dataset is a road layer. Just scroll down and you can find it under Frequently Requested Datasets. You can save it directly to your original folder by right-clicking the link the same way you did earlier on the Natural Earth website. If you accidentally save this file to your Downloads folder, that's fine. Just copy and paste it to your original folder. The next dataset you need is the fire hydrants. Just scroll down to the fire plan data and download the fire hydrants shapefile. When both zip files are in your original folder, use 7-zip to decompress the contents. Remember to delete the zip files when you are done. ArcGIS Pro doesn't always keep track of the changes made outside of the program. To let ArcPro know about them, just refresh the original folder. Drag and drop the road layer from the original folder directly onto the map. I know that my fire hydrants are going to be in Eureka, so I'm going to zoom in a bit. Next, I'm going to check the spatial reference of the Datum Shift pane. Go ahead and open the Properties and navigate to the Coordinate Systems tab. Because the Humboldt County road layer was the first one added to the map pane, it should adopt its spatial reference information. As you can see, the Datum Shift pane is using the state plane coordinate system. You'll see that this matches one of the coordinate systems listed under the Layers group. The other coordinate system belongs to the default Esri base map. If for some reason the Datum Shift pane is using a different spatial reference system, you can change it now to State Plane California 1. Let's get back to the map. My roads turned out green, so I'm going to change the color. You don't have to do this, it's just my personal preference. Go ahead and add the fire hydrants to the map as well. Here I'm also going to change the symbol and color. You might want to change yours as well because the color of the fire hydrant will matter in a later step. Next, just zoom in a little closer so that you can see the individual fire hydrants. Next, we're going to make a copy of the fire hydrant layer that uses a different spatial reference system. To do this, you need to use the Project tool. To find it, click the Tools button on the Analysis tab and type in Project on the search bar of the Geoprocessing pane. For the input, add the fire hydrant layer. I'm going to change the name of the output so that it says Hydrants. Instead of a projected spatial reference like the state plane coordinate system, this copy of the dataset will only use a basic geographic coordinate system. Locate WGS 1984 under the World folder on the list of geographic coordinate systems. When you're ready, go ahead and run the tool. ArcPro usually adds the data to the map automatically. It's hard to tell because it's using the same color. Go ahead and change the color of the new hydrant layer so that you can tell it apart from the old one. Now, to see the datum shift, you're going to have to zoom in really close. Now you can see two triangles. The pink triangles are the original fire hydrants, and the blue ones are the ones that don't have a map projection. You'll notice that they appear in slightly different locations. I'm going to click on them to pull up their information just to check that they are the same fire hydrants. Yes, both of these are fire hydrant number 1143. So this is what I mean by a datum shift. You have two layers with different spatial reference systems. ArcGIS Pro tries to line them up using Project on the fly, but it doesn't do a perfect job. Use the Measure tool to check the distance on the ground between these two datasets. As I mentioned before, Project on the fly is inconsistent. Sometimes there's no visible datum shift. If that happens to you, that's fine. Just make a note of it in your report. Okay, so the written instructions ask you to answer two more questions. Copy and paste them into your Word document and do your best to answer them. Exploring the PRJ file. Okay, so by now you should have a sense about the accuracy of spatial data sets. Even if it can't be avoided, you should at least be aware that these types of spatial errors can occur and do your best to look out for them. In this next step, we're going to tackle a different problem. From time to time, you may come across a data set with an unknown spatial reference. When this happens, ArcPro won't know where to place the layer on the map. So why does this happen? Most often, it's because of poor file management, and a small piece of the overall shapefile got lost. This piece is called a PRJ file. You already learned that a shapefile is made up of several related files. In ArcPro, they look like one file, but if you look at them in Microsoft Windows File Explorer, you can see all of them. Because of carelessness or inexperience, sometimes these files get separated, which corrupts the shapefile. One of these files, the PRJ file, lets ArcGIS Pro know what spatial reference system the shapefile uses. Let's look at the contents of the PRJ file. In Microsoft Windows, go to your original folder and right-click on the Populated Places PRJ file. Choose Open With and use Notepad to open the file. As you can see, a PRJ file only contains text related to the spatial reference system. It's not important that you understand everything in this text file. All you need to know is that this file is necessary for ArcGIS Pro to place data on the map. Don't delete it or misplace it. Now that I just told you not to delete it, that's exactly what we're going to do to see what happens. Close Notepad and delete the PRJ file for the Populated Places dataset. Next, go back to ArcPro and refresh the original folder. Drag the Populated Places shapefile from the original folder directly onto the map. To see where it ended up, I'm going to zoom to the layer. Okay, so it sort of looks fine. The cities are relatively in the correct positions as they are related to each other, but where are they on the map? I'm going to zoom out to find out where it landed. So if I zoom way out, you can see that the points are gathered off of the California coast. Now remember, these are supposed to be cities around the world. Not only are they in the wrong place, but they are way too small. All of the cities are gathered into one tiny region. This is what happens when you misplace or delete a PRJ file. I noticed that I never got a warning message, which is unusual. ArcGIS Pro usually sends you a pop-up warning message when a layer has an unknown spatial reference. Okay, so if you encounter this problem, how do you fix it? The sad thing is that it's not always possible. You have to know exactly what the original spatial reference system was. If you get it wrong, your data will still be in the wrong place. Okay, so assuming that you know what the original spatial reference system was, you can use a tool called Define Projection to recreate the lost PRJ file. Pull up the geoprocessing pane and search for the Define Projection tool. This tool is as simple as it gets. All it wants is an input data set and a coordinate system. So the input data set is the populated places. To choose the right coordinate system, think back to the original PRJ file. It was GCS WGS 1984 and no map projection, just the basic geographic coordinate system. So that's what we need to enter into the Define Projection tool. Once we run the tool, it replaces the PRJ file, and now ArcPro can plot the cities on the map. There is one last section in the written instructions called Avoid confusing the Project tool with the Define Projection tool. This happens all the time. These tools do completely different things, but because of the names, people mix them up, and it screws up their data sets. So take a moment to read through this section of the written instructions. After that, save your project, your Word document, and your Excel table. Be prepared to turn in your results in whatever way your professor asks. If you liked this video, give it a thumbs up and subscribe. Thanks for watching.